Welcome to Hot Chips 26. Session 4, ARM servers.
Right. Good afternoon, everyone, and welcome to the ARM servers session. My name is Stefan Russo from Intel, and I'll be hosting this session tonight. The first paper is entitled the AMD Opteron Seattle, a 64-bit ARM dense server processor. It will be presented by Sean White. Sean is a fellow at Advanced Micro Devices. Since joining AMD 12 years ago, he has worked on numerous processors and chipset products and currently works as a system-on-chip architect for upcoming AMD server processors. Sean has over 20 years of experience in computer design, having worked on mini computers, servers, and workstations at Data General, multi-processor servers at Axial Computer, and the first shipping hypertransport chipset at API Networks before he joined AMD. He holds a bachelor's degree in physics and a master's degree in electrical engineering, both from Worcester Polytechnic Institute. Please join me in welcoming Sean White.
Thanks, Stefan. Afternoon, everybody. There we go. Okay, some of you have probably seen some of the press that AMD has put out about our Seattle chip. Let me talk a little bit about what it's going to be. It's our first 64-bit ARM server processor. We do use some ARM technology in some of our x86 parts for some security, but this is going to be the first part that the OS boots on the ARM parts. So it's going to have 8 ARM Cortex-A57 cores, 2 DDR channels, a variety of I/O that I'll talk about in some detail in the following slides. It's going to be a 28-nanometer part built at Global Foundries. I also want to put a little bit about why are we building the part. So when you look at the applications you see in the data center out there, there's actually a fairly wide range. There's HPC where you're just putting through something that looks like LinPack. There's databases where you're crunching hard on some database in a cache. There's also kind of more and more these days applications people kind of lump together as cloud. These applications, you see a lot of them, when you profile the application, actually has, compared to traditional big iron server processors, it actually has kind of a crappy IPC, instructions per clock. And it actually has data sets that are not necessarily friendly to the large caches that go on like an Opteron or a Xeon. What you see is you could actually get as much throughput. The example I'll give is, say, like you have a search engine. So you have, you've sharded it out across all your nodes in your data center. You've got, say, a small instruction footprint of a meg or two, and all that instruction is doing is waiting for a query to come in from the network and then searching, all the tables it has in memory, and it's got the memory filled up with whatever the dictionary or table set that it wants to search is. So that's going to be gigabytes of data. It's filling up the memory. That's not going to fit no matter how much silicon you devote to an SRAM cache. That's going to bust it. So if you're not getting any advantage of having a really high power, high IPC core, you're not getting any advantage of having a lot of cache on the chip because your application just natively is missing in the cache all the time. You can get just as much throughput with a piece of silicon that's designed for a different point. It can have a lower IPC core, it can have smaller caches, but still do very well on these types of applications, and then you can save the power and silicon area. So that's the, kind of the elevator pitch for why this part is designed the way it is. The other kind of more strategic thing is, transitions to 64-bit are a big deal. They don't happen in industry standard instruction sets every year. So as most of us remember, it was a big deal when x86 transitioned to 64-bit, and AMD was leading when that happened. It's going to be a big deal that ARM is transitioning from 32 to 64-bit, and AMD intends to be one of the leaders in that transition as well. And this is the first of several parts that people will see from AMD, trying to lead where that transition is going to go. This might be a little bit of an eye chart, but hopefully everybody has this has this locally. So this is kind of the simplified block diagram, showing what's in the part. Get a laser pointer. So as I mentioned, we've got 8 64-bit A57 cores. So each of these is configured basically as a dual sharing a 1 meg L2. So I can think of this as four duals connected together with a coherent fabric. The coherent fabric contains 8 meg of L3 cache. There's a variety of I/O. PCIe, SATA, 10 gigabit Ethernet are the high bandwidth interfaces, but there's also some lower speed utility devices. We have 2 channels of DDR3 or 4, depending what the system vendor chooses to build. It's going to be in a BGA package, about 27 millimeters on a side. And we have some additional things in there. We have an integrated Cortex A5, which is a 32-bit core. That gives us kind of integrated system control management features that that can interface with the chassis management in a data center environment. We also have a cryptographic coprocessor that has a bunch of encryption and decryption capabilities that jobs can be offloaded from the 64-bit cores to be executed on there. So down the side we have kind of a summary of what all the bits and pieces are. A little bit more on the memory. Like I said, it's out a laser pointer. It's got 2 channels, supports ECC, 2 DIMMs per channel, up to 1866 for the speeds. Supports a variety of DIMM types. If you fully populate the memory system, you could have up to 128 gigabytes hanging off this chip. For the integrated I/O, we have 8 lanes of SATA, up to 6 gigabits per second, 2 lanes of 10 gigabit Ethernet, 10G base KR, 8 lanes of PCI Express supporting up to Gen 3 and a variety of subdivisions. The SCP gives us security and management features, and the CCP giving us our cryptographic functions. I didn't have a nice die picture, but I do have a package picture for people who are into that sort of thing. So here's kind of the simplified block diagram of how things are connected together. As I said, we have, sorry, having laser pointer failure. We have the Cortex A57s, the kind of the 4 duals connected to a high-speed coherent fabric that hooks all the high bandwidth devices together. We have SATA, 10 gig Ethernet, a DDR channel on either side of the chip. We have a bridge to a number of lower speed I/O devices, and then we have kind of a little bit of a complex, we have PCIe, we have a DMA engine, and then we have some connectivity for the system control processor. It's a little complicated so that the CCP can be shared by both the SCP and the 64-bit cores. Here's a cartoon of the what the die floor plan looks like. So you can see where the major blocks in the design are. Over here is on the left-hand side is the SCP and the CCP. Okay. So the complex that we have put together, as I said, each think of the Seattle A57 configuration as two A57s sharing a 1 meg. It's ARMv8 architecture. The level of caches that are built into the core, these are mostly ARM's choices for some of these. Some of these are configured by AMD using this IP. So 48K L1I cache, 3-way set associative, protected by parity. 32K L1 data cache, 2-way ECC protected. 1 meg shared L2 cache, which is 16-way with ECC. 8 meg shared L3, 16-way, also protected by ECC. And there's an additional Snoop filter kind of integrated into the coherent fabric with the L3 cache. So our implementation includes the optional cryptographic instructions that the A57 may or may not support, depending on how ARM's customer chooses to build the IP. In addition, we have kind of the standard core site debug and the standard interrupt controller that are used in the ARM SoCs. So the memory system, as I mentioned before, is we have two interleaved DDR3 or 4 DRAM channels, depending what the system vendor wants to build. 72-bit data path on each channel, so 64 bits of data plus ECC. 1 or 2 DIMMs per channel. We support registered DIMMs, SO DIMMs, UDIMMs, unbuffered DIMMs. Again, up to the system designer. That gives you up to 128 gigabytes attached to this BGA. DRAM controller clock runs at about 1/4 of the data rate. So, for example, DDR3 1600 would be running the controller at 400 megahertz. Supports SecDed, single bit error correct, double bit error detect ECC. Correctable errors are handled inline before returning data to the cores or I/O. PCI Express, we have 8 lanes of PCI Express. We can configure that a couple different ways. You can have a single by 8, you could have 2 by 4s, or you could have a by 4 and 2 by 2s. Again, it's up to the system vendor, depending what devices or slots they want to support. If you have a configuration where you have multiple controllers, each one supports Gen 1, Gen 2, Gen 3 operation independently. And then the message signal interrupts from PCIe are tied into the GIC, the generic interrupt controller. This is a little busy, but it's not that complicated. This is just showing that we have a 10 gig Ethernet controller. What we're actually showing here is we have kind of 2 of them mostly, and then a shared 2-lane PHY. The PHYs we use in this part are 2 lanes. So in this configuration, you have most things duplicated at the control and PCS layer. Then they come together at the PHY. So 10G base KR is kind of a 1 meter copper PCB channel for Ethernet and dense servers. Also supports lower speed at 1000 base KX, 1 gigabit, and it has some offload acceleration features. SATA, again, fairly straightforward controller driving 8 lanes. So SATA Rev 3 compliant, supports Gen 1, Gen 2, Gen 3 independently on each of the SATA lanes. Cryptographic coprocessor, a little more detail on this. As I said before, it gives you some encryption, decryption, compression, decompression, offload capabilities. Specifically, gives you AES, ECC, RSA, SHA, zlib compress and decompress, and it has a hardware random number generator. This is kind of a dual-ported device where there's a secure port into it from the SCP. So at boot time, when you're trying to do a secure boot, the SCP can use it. The A5 is not a really powerful processor, but it can offload a bunch of the authentication and cryptographic functions that it wants to perform to make sure it's doing a trusted boot and make use of the CCP. Once the system boots the 64-bit cores and they're running an OS, the A57s can queue non-secure jobs onto the same hardware. The system control processor is actually kind of a small SoC within the SoC. It's got an A5, Cortex A5 core. It has its own GIC. It has its own 1 gigabit Ethernet with RGMII. It's got a 64K ROM. This is kind of the root of hardware trust. This will, the SCP will boot locally off of this, and this has enough instructions to authenticate any off-chip boot that it's going to do. It's got 512K of local SRAM protected by ECC. It's got trust zone capability, so it can split that 512K into secure and non-secure regions. It's got a bridge to the coherent fabric, and it's got a variety of simple or low-speed IOs, timers, I2C, GPIOs, SPI ports, UARTs. So there's a variety of ways that can be hooked up to kind of chassis system management functionality. This is kind of a little more detailed list. The picture on the previous page, Cortex A5, 64K ROM, 512K SRAM, 10100 1 gig Ethernet. Interface to, I guess it's the other thing, kind of the clock reset power management functionality is controlled by the SCP firmware. So if it wants to turn off power to the whole rest of the chip and just wait for the chassis management to tell it bring your node up and ask have it boot an operating system, you can control that directly through here. You can kill clocks, you can kill power to the rest of the chip. It also has core site debug capability, controls several GPIOs, has an interrupt controller, I2C, SPI ports, timers, UARTs, and a bridge to the coherent space. So if it wanted to talk to some of the high-speed IOs directly, it can. So here's, from my software friends, here's a little bit of how the boot flow works. So the SoC powers on, and at power on, the SCP comes out of reset, and it boots from the on-chip ROM, which by default is secure. It's hardware. That was frozen when we shipped the design to the fab. That bootloader will fetch from an off-chip ROM, and that will be authenticated. That will start initializing the SoC. Next step is to initialize the memory controller, and then it brings up a little real-time OS to run on the SCP, and that can do a variety of things while the system's running. SoC management, power management. System management control, RAS functionality, console, and it can also, if your chassis management is telling the SCP, boot the 64-bit cores, it can copy, the bootstrap for the 64-bit cores over to memory and release the A57s from reset, and then they'll do their OS boot. So where we are right now, this is a little bit of a preview. Not everything that everybody wants to know about Seattle is in these slides, because we're still a short while away from actually the real product launch. But we are, given that this is an important transition, we are actually sharing kind of pre-production hardware with key customers, key partners. If somebody wants to develop a 64-bit ARM OS, they need hardware to develop on. They can try to do what they can with cross-compiling and some other things, but the functionality we have with prototype systems is still very useful for some of the key people to get into their hands. So this, if you're one of those key people, or you think you are, you should give us a call. This is what the box looks like that we're sharing with our customers ahead of the production launch. So it's kind of a single processor, 2U rack mount chassis. We're supporting just DDR3 in 1 or 2 fixed configs. We have a couple of configurations for PCIe supported. Supports up to 8 hard drives, and has kind of a simple system management interface that people can talk to the SCP. Here's actual photo of the actual board that we're sharing with people. It's a micro ATX form factor. There's WUD Seattle on the system. The DDR as I said before, 2 DIBs per memory. Have a couple of PCIe options. You get all 8 SATA ports. You get 2 Ethernet connections, number of I2C, UARTs, and a variety of debug features that wouldn't be on a shipping system, but are useful to AMD as we're doing silicon validation, useful to our partners as they'll be working with us before things are really production solid. And that's it. Like I said, I can't share everything because we're not at a final product launch yet, but I wanted to share the details that I could ahead of the product launch, and show people that we have some real hardware in hand that's doing some interesting things, and I'll answer whatever questions I can. So if any people want to go to the mics, I'll see what I can do.
Nathan Brookwood, Insight 64. On the cryptographic coprocessor.
Yes.
There you go, CCP. Why did you include that? Aren't most of the cryptographic functions already embedded in the ARM v8 architecture?
They are. Like I say, the way I think of this is, you have 8 cores. Some of the jobs that this thing is kind of dedicated to do, would take up the whole core. So it is a way to, kind of have an offload engine. If nothing else, think of this as a, kind of a lightweight DMA engine that has these encryption and compression capabilities on it. So it's not necessarily giving you a ton of horsepower, but if all you were doing was a simple job that could be offloaded, it frees up a core to do something more valuable, more complex than just one of the repetitive ECC or AES tasks.
And where did the IP for that come from? Is it homegrown?
We're, outside of the A57, I guess, we're saving some of the details about exactly what came from where. Obviously, the A57 came from ARM. There's a mix of IP in the design that came from within AMD and from, obviously places outside AMD. We're not disclosing those exact details right now, other than the A57, obviously.
Okay, thanks.
Let's take a question from the other side of the room, please.
NVIDIA.
Did you say what the power consumption was?
No, that will, power, frequency, price, those are going to be launch details that, that we're not talking about today.
And the ECC, does it cover the data and the tag arrays?
Yes.
And is there a reason why there is no ECC in the iCache?
Yes. So the iCache, if you take, if you think about it, the iCache is unmodified instruction data. So if you fetch that, you have your parity protection. Your parity says you have a bad cache line. You just drop it, refetch from main memory, bring in a new good cache line. You don't need to do the inline correction.
Thank you.
Okay. We have one more question here.
Well, I was going to ask a question similar to the last person, but hopefully, despite the cannot answer, you can give some guidance. By the way, Ben Ekman, Freescale. So do you, from a power perspective, the reference designs you showed had fans, so obviously fans are required given the power levels, so it's greater than, I don't know, 10, 20, 30 watts. Any rough information you can give there?
No rough information.
Okay.
It's meant to be lower than a traditional Opteron or Xeon, but
Understood.
Not giving specifics today, I'm afraid.
And then I guess I had similar questions frequency-wise, where if this is a 500 megahertz product, it doesn't stack up against a Xeon. If it's a 3 gigahertz part, it looks great. And where does it lie?
It will be between those two data points.
Yes, please.
Yeah, Bill Rash from Intel. I wanted to ask about the memory RAS. You mentioned ECC. Do you have anything like a chip kill recovery or something similar as well?
No. This has we do in our other parts. In this particular part, we just have kind of basic SecDed ECC.
Okay, thank you.
Abhijit, Texas Instruments. Can you share any more details on the current interconnect? Is it in-house? The interconnect, is it the ARM solution or is it something in-house?
Not today.
Okay.
At launch, we'll speak about things in greater detail.
Thank you.
Mike Brizzoni from Camp Marketing. So in that reference platform, I saw a cluster toy, storage server toy, an ARM port of Ubuntu or Fedora optimization device.
Is there a question in there?
Yes. I'm trying to figure out where you're taking this, and certainly we saw your cold storage solution at Open Compute. I'd also like to ask two questions. One, the question I asked to Mr. Mueller earlier: what can be optimized within the ARM architecture to give it utility benefits from an applications perspective versus the Intel product line? And two, what Intel product line will you be positioning this product against?
So this is a place I'm not sure any of the traditional server players are playing right now. Like I say, this is meant to be kind of a very dense, very integrated single chip solution. It is meant to be in a lower power band. As I lost the slides. As I said in the kind of why are we building it? What's the elevator pitch? There are more and more of those applications that are showing up in big data centers. People build buildings full of racks of machines to hit some of these spaces, and they don't look like a traditional high IPC fit in the cache database kind of workload. They'll actually run well on this part at a lower power than they would on kind of the big iron part. So I think there's differentiation we can do there. Which we're doing in this part. looking forward, or even looking at this part, the I/O here is a little bit of a Swiss Army knife. We have, basic, networking. Maybe not basic. Networking up to 10 gig. We have, SATA up to 6 gigabits, and we have PCIe for everybody else who has a favorite card they want to plug in that doesn't match one of those interfaces. And it's all integrated in a single chip. So, we can do more of that as the market for these spaces comes into existence. We can adjust our roadmap to say, okay, these are the I/O interfaces that are most valuable. We can change the SoC design to do that. For a customer that's motivated enough, AMD can work with them like we did with Nintendo, Microsoft, and Sony on the consoles to say, if you want to customize an SoC to be exactly what you want, or to put on a piece of your IP that adds a lot of value, you can do that here. I don't know that Intel has that flexibility to do that sort of thing. So I think there's plenty of innovation we can do in the SoC space. I know there are innovations outside the within the core that ARM, AMD, and other people in the ARM infrastructure are working on as well.
Thank you very much.
All right, so let's thank Shang again.
Thank you.
So the next paper is entitled ARM Next Generation IP Supporting Avago High-End Networking, and will be co-presented by Mike Filippo from ARM and Raghu Kondapalli from Avago Technologies. So Mike is the lead architect of ARM's high-end CPU, including Cortex-A57 and follow-ons. Prior to this role, Mike was the lead architect of ARM's Enterprise System Interconnect family and co-architect of AMBA5. Before joining ARM, Mike was involved in the design of Athlon and Opteron products at AMD, as well as server and supercomputing products at Intel. Raghu is the Director of Technology focused on strategic planning and solution architecture for the Network Solutions Group of Avago Technologies. Most recently, he was the founder and CTO of a cloud-based video collaboration company called Cloud Grapes, where he was the chief architect for the cloud-based video as a service solution. Prior to Cloud Grapes, he led technology and system architecture teams at Marvell, Nokia, and Nortel. He has about 35 patent applications in process. He received a master's degree in electrical engineering from San Jose State University and a bachelor's degree in electronics and telecommunications from Osmania University in India. So please join me in welcoming Mike Filippo and Raghu Kondapalli.
Okay, thanks, Stefan. So, as Stefan mentioned, today's presentation is going to be a co-presentation between ARM and Avago. So I'll take a few minutes to describe to you ARM's next-generation 64-bit CPU IP and the enterprise system IP that goes with that, and then Raghu will follow up with the implementation of that IP in Avago products and some more details there. So just a little bit of context, a little bit of background here. So ARM has historically been focused in the mobile market. In the last 2 or 3 years, though, our ecosystem and the performance and the power efficiency that we can bring to bear have allowed us to make a pretty significant move into the enterprise market as well in the area of servers, as you heard about, as well as high-end networking. So the number of new products that are enabling that are a combination of our CPUs, Cortex-A57 and Cortex-A53, so scalable coherent interconnect products in the Core-Link CCN 504 and 508, and then the architectures underlying that, basically ARM v8A and the AMBA5 CHI architecture. Again, all of this combining together to allow us to make a move, basically expand our market share going from mobile into the enterprise space as well. All right, so let's take a minute and just give you some information on the next generation CPU IP that we have here. So actually, Sean and I should have talked. I think, before we present it here, because he presented a lot of this information. I'll cover it and try not to repeat too much of what Sean said. So what you see in the A57 and the A53 is a continuum of performance and power. So at the high end, basically A57 is ARM's highest performance 64-bit CPU. Obviously, it's 32-bit capable as well, but for the purpose of this presentation, I'm focusing on the 64-bit capability in the enterprise space. So A57 is a 3-wide 3-wide dispatch, 8-issue, fully out-of-order machine, fairly high-end out-of-order machine. Again, targeting high performance at good power efficiency. Contrast that with A53, which is the most power-efficient ARM CPU available in the A profile. A53 is an in-order 2-wide machine that, again, is really, really targeting extreme power efficiency. So the combination of those two guys really allows us to have, like I said, a continuum of power and performance depending on what's required for the application. So, for example, we have basically the industry's first capability of doing heterogeneous multiprocessing, or what we call big. LITTLE MP. So the big. LITTLE MP, that technology has been around. A57 and A53 are the second generation of that, but really what it comes down to, what this enables is you can put A57 and A53 as peers in a coherent system. They'll talk together. The OS can schedule threads to each one of them. Effectively, it's seamless, coherent communication. So what we do with big. LITTLE MP is exactly what you would expect with a heterogeneous multiprocessing capability of ensuring that applications run on the silicon that's most appropriate for the power and performance requirements of the application. So allowing a significant span of performance and power. For example, just to give you some context on the performance and power of these two guys, if you take something like A57, put it into the CCN 504 or 508, which I'll talk about in just a moment, those being 16 CPU and 32 CPU systems, we got a path to between 190 and 200 spec-int rate 2006 at about 17 watts. So I guess just to make sure we're all on the same page here, that spec-int, call it non-gamed. Call it kind of where libquantum is normalized. We all like to play games with spec, but the reality is if you run GCC on the GCC compilation of that, you're looking at somewhere approaching 200 spec-int rate 2006, again at about the 17 watt mark. Contrast that with A53, which is about, again, a 16 CPU system in a CCN 504 or 508, is right at about between 90 and 100 spec-int rate 2006 at about 5 watts. So a good range, again, allowing system SoC vendors and users of that to be able to, again, target the application at the power and performance profile that's most appropriate for them. Okay, so let's take a minute and we'll move on to ARM system IP. So yeah, this is definitely an eye chart. I'll call out the important aspects of it. So ARM delivers quite a bit of system IP. I'm going to focus on one piece today, the CCN 508, but I just want to take a minute and kind of walk through just a few examples of what we provide. So you look at something like our virtualized interrupt controller, the GIC 500. We have non-coherent interconnects in the form of the NIC 400. We have a system MMU, the MMU 500. We have enterprise memory controllers in the DMC 520. And then finally, all of that really sits around the CCN 508. So ARM system IP, we push for breadth and make sure that we're covering effectively the commoditized portions of the IP, enabling our partners to do the right things in the areas that are room for areas for differentiation, like Sean described earlier. So let's take a few minutes now and walk through some of the aspects of the CCN 508. So this is the follow-on to the CCN 504. It enables up to 8 processor clusters, each cluster, like I referred to in the A57 and A53, being from 1 to 4 cores. So this is basically a 32 CPU system. It has 4 ports targeting memory controllers, enabling basically memory bandwidth up to about 25 gigabytes per second per port, targeting between 80 and 100 gigabytes per second total memory bandwidth in the 508. The transport layer shown here, so this is a ring microarchitecture. It is fully distributed, meaning that there's no centralized point of arbitration, no centralized point of control. Basically, every cross point that you see here knows everything that it needs to know to be able to take a message in, route it over the transport layer, and get that message off. So a relatively straightforward microarchitecture. It's also an implementation-aware design, meaning that this thing is intended to run at core frequency. So we have, like I said, it's a ring microarchitecture. It comprises 5 bidirectional rings, basically supporting the AMBA5 CHI virtual channel requirements. So while these are defined as VCs in the architecture definition in AMBA5 CHR, we actually chose to implement physical channels to meet the bandwidth requirements of the CCN 508. It includes 4 128-bit data rings, so it's 2 sets of bidirectional data rings, enabling around 2.9 terabits per second peak and about 1.8 terabits per second sustained throughput. So looking at the rest of the system, you see these blue boxes here, again, a bit of an eye chart. These are labeled L3. It's a bit of a misnomer. The reality is that includes an L3 cache or system cache. It includes a point of coherency and a point of serialization, and includes a snoop filter. So like I said, 8 partitions of those, ranging from 1 megabyte to 32 megabytes total capacity. That's, again, the combination of all of those is that capacity. So like I said, the L3 is both acts as a cache for compute as well as I/O and acceleration. It also includes point of ordering and point of coherency, basically as a front end to the DRAM. It includes an integrated snoop filtering for coherency scaling, effectively to mitigate the quadratic coherency scaling that you otherwise see in the absence of a snoop filter. And then it also includes adaptive inclusion and exclusion policies, effectively minimizing the amount of redundancy between the L2 and the L3 caches. So moving on, the CCN 508 includes 8 I/O bridges. So these are the yellow boxes up here. Each of those bridges has 4 ACE light ports. So ACE light is our architectural definition for I/O coherent traffic. Effectively, these are for I/O coherent mastering devices. So 8 bridges, 3 apiece, so up to 24 ACE light ports. Each of those, like I said, are I/O coherent and have support for SMMU, basically. Each of these bridges has support for about up to a little over 320 gigabits per second per bridge. So the combination of all 8 of these is actually more than the total available interconnect bandwidth. And the reality is we expect partners not to be using all of that bandwidth at once, but basically to be using these, as you would expect, for I/O accelerator devices to have them in a phase type of functionality. The L3 cache that I described earlier can be used as a flexible I/O cache. So on a per transaction basis, any I/O devices or accelerator devices that are sitting outside of our I/O bridges can choose to use the L3, cache in the L3, or not cache in the L3. And again, that's on a per transaction basis. And then finally, we've got pretty extensive integrated system clocking support. A few examples of that are some source synchronous, asynchronous bridges. As you would expect, there's going to be quite a bit of asynchrony at the boundary periphery of the CCN 508, flexible clock ratios, and then quite a bit of additional IP effectively to allow partners to converge timing reasonably easily. All right, so a few other points on the CCN 508. So it has system-level QoS basically from top to bottom, from every ingress point to the egress point. That starts with optional QoS regulators at the ingress points where a user can set those up to meet specific latency requirements and bandwidth requirements, and QoS regulator will drive the appropriate values into the interconnect, ensuring that those latency and bandwidth requirements are met. It includes, throughout the entirety of the microarchitecture, it includes prioritized arbitration and microarchitecture to eliminate head-of-line blocking at ring upload and download points, at the I/O, basically ingress into the I/O bridges, the arbiters and the schedulers for the I/O bridges, and then quite a bit of fairly sophisticated microarchitecture in the L3 in support of QoS capability. And then finally, actually underlying all of that is AMBA5 CHI has QoS capabilities built into that in the form of QoS values that are propagated throughout the interconnect, as well as a hybrid retry-based protocol layer flow control capability that is somewhat fundamental to our QoS handling here. So in addition to QoS, the CCN 508 has fairly extensive power management features in the form of way shedding. So we have a 16-way L3, 16 ways per partition. Those can be configured to run at effectively 8-way set associative mode, basically cutting that L3 size in half. It can also be configured to remove that completely, but throughout all of this, the snoop filter remains active, and all of these modes are available effectively while the system's running full bore. So you can yank a pin or send in a specific configuration command, and all the flushing and the basically cleaning and validating everything else happens while there's significant other traffic going on. This is all basically hidden. So it's, we did quite a bit of work to make that as easy for the user to utilize as possible. And then finally, there's means of low latency retention control, basically, in-pipeline retention control to allow the L3 to be put into and taken out of retention effectively in the active access pipelines. All right, so I've just touched on a few pieces here in the CPU and the system enterprise space, basically, how we're enabling our partners to push the envelope in compute and system capabilities in the enterprise space going forward. So we talked about the Cortex-A57, the Cortex-A53, and the CCN508. CCN504 is similar in that is in the family of CCNs as well. But in the end, really the ARM ecosystem is all about what our partners do with that IP. So we work pretty extensively with partners to enable them to have innovative products using that IP as well as combined with their own. So an example of that, my colleague Raghu Kundapalli from Avago is going to follow up there. Thanks, Raghu.
Mike. Hello, everyone. Let's see. I guess the rest of the presentation I'm going to try to cover in the few minutes an overview of our Axia platform itself, the architectural aspects of it, and the most latest instantiation of this architecture referred to as 5516, which has 16 A15 cores. And I will cover some of the software aspects of it. And as part of the platform architecture, I'll try to illustrate some of the networking applications, data and control plane applications, how this architecture helps. So I guess the macro picture is as we are the power efficiencies and the scale-out paradigms of data centers and mobile networks thrive, right? One of the fundamental issues is to be able to create these disruptions or allow these data centers and mobile networks to scale to massive scale. And typically, these are all bundled under the terms of software-defined networking, SDN, or network function virtualization, NFV, right? So if you look at the essence of these emerging trends, they are seeking for an option to be able to disaggregate the network functions from a network element and map them onto virtualized network processing elements, right? So that's the essence of these. And then given the varying types of workloads, whether it's data control and the different types of network elements typically that are put together, like routers, base stations, switches, appliances, etc., right? There are some common characteristics for each of these network processing elements that stand out, which are, for example, one of them is programmability, right? These has to be very highly programmable. Second one is specific function acceleration. Once you have disaggregated a network function, you have to be able to accelerate that function. And then one of the other important aspects is the flexibility of being able to process these network functions in a indeterminate order prior to a network element is put together. And then, of course, the last part is the rich set of software APIs to be able to put together solutions on top of the hardware that we are all building. So Axia platform in general has been envisioned in many of these aspects that are listed here to offer sort of a balance of how do you offer programmability, flexibility, and a set of APIs to be able to integrate software, faster time to market type of thing for both data and control plane applications. And then if you zoom in a little bit further down, one of the fundamental aspects that gives scalability to this Axia platform is what is referred to as virtual pipeline autonomous processing, which essentially couples the CPU clusters and variety of these accelerators, either it could be coming from Avago or it could be some customer IP that got integrated into a particular SoC, like DSPs or some other IPs. So a combination of all of these accelerators and CPU clusters are tightly coupled using this technology. In general, we refer to as virtual pipeline processing. So I guess the challenge for each of these, when you put together a network element like this, is to how do you create the functional acceleration that we were referring to, and the flexibility in these to address these enterprise workloads, right? So many of our competitors also have these compute clusters, these accelerators. I think the fundamental difference in this Axia architecture is how these are put together makes a big difference in terms of the performance per watt advantage that one would get in these sort of enterprise workloads. If you look at the three of these models are shown here for a microflow of packets coming into an SoC, where it flows through from engine 1 to 3 to a CPU to another engine and goes out, right? That's the flow of the packets. So there are many ways to implement this. One is non-pipeline way, in which obviously the CPU manages the inputs and outputs of each of these functions, which tends to be time-consuming and lower in performance. And the second one is fixed pipeline, where one would have to traverse through many times within this pipeline to really achieve all the steps that are needed for this functional acceleration. And the third one, which is the virtual pipeline, we're referring to as sort of a more intelligent way where autonomously you want to be able to attach each of these accelerators so they can flow through easily, including the CPU, right? Can be stitched together on a per microflow basis. So an example of this, which is typically used in many of our customer use cases, is if you wanted to decrypt a packet, incoming packet for a flow, decrypt it, look at the inside headers, and then do further processing on it, either classify and take further actions on it. And then on its way out, you re-encrypt it and send it out, possibly even change some header fields, etc. So if you look at the usage models, whether it's a traditional vertically integrated network element where you have, or it could be a horizontally disaggregated, sort of a functionally disaggregated network element, right? The flexibility in processing order is key, and then how these CPU clusters talk to these accelerators is another key aspect. And then as the packets come in, right, each of these network elements, the packets may need to be inspected, protocols need to be terminated, headers need to be modified, maybe there are many other functions like that. So Axia offers a distinct advantage compared to other multi-core architectures in being able to utilize these accelerators either in a pre-processing, post-processing, intra-processing, or a fast-path processing models. So some of this is a little bit of an eye chart. Some of these are listed here where I'll quickly try to go through a couple of these examples. For example, a fast path would be a great example for Axia, which has, at least the current instantiation of it has 160 gigabits worth of switching capacity. So if the packets are coming in from one port, going out another port, pure switching, switch traffic manager, forwarding, and then go out, then there is no CPU involved. There's no other path that needs to be touched. So we call it as a fast path. It could be pre-processing, for example, if you're trying to load balance traffic headed to the CPU and shape it as it goes into CPU for further processing. That's a good example of a pre-processing. Or intra-processing, where it's a classic look-aside model where a lot of these security and other accelerators operate on typically. And then the last one is a post-processing, which is if the packets are originated from this network element going out, if you need to encrypt them, if you need to make up headers, all of that can be part of the post-processing model. And so some of the highlights of this Axia architecture are this is the sort of the first high-end 16-core ARM, A15-based ARM core SoC, which is fully coherent, and it has market-leading accelerators and a variety of packet processing capabilities. It has, like I was saying before, 160 gigs of Ethernet switching capacity. And the interesting thing here is also that once the parts have been shipped within a couple of days, Linux was up and running, and customer was quite happy with that. So if you look at the overview of this, there are 4 CPU clusters, each consisting of 4 A15 cores, sharing a 2 meg L2 and 8 megs of L3. Other than secure boot and all that, it has an interesting component called NCA, Network Compute Adapter, which supports sort of flow-aware load balancing, ordered and atomic functionality for traffic, including the cores that are on the device, on this SoC, and also if it were to be connected to an external host for those cores as well, through the PCIe or something like that. So this part has been sampling since Q3 of 2013, and it's made in 28-nanometer technology. So this is a picture of the board, evaluation board that gets shipped. It's an AMC form factor. It has a variety of connectors, and also it supports full synchronous Ethernet and 1588 timing for some of the critical applications like base stations. That becomes very important. And it has a variety of power management options to be able to turn off all of these clusters and be able to reduce the power. So I guess along with the hardware, there is a software aspect of it where Avago offers a variety of simulation tools, real-time environments where these are device drivers, application development kits like for wireless transport, mobile backhaul, aggregation, and we work with a variety of third-party software companies to be able to integrate sort of the fast path engines along with the rest of the hardware. And then last, like I was saying before, there are a rich set of ADKs that Avago delivers either in partnership with customers or natively on our own as a standard product, which sits on top of the drivers that we support for our hardware, and then the rich set of APIs. Many of these APIs are fairly standards compliant, for example, OpenFlow, et cetera. And some of them are leaving enough differentiation for extensions to be able to add end product differentiation. I guess in summary, right, so this is the first 16-core ARM SMP-based processor that is in the industry today. This is based on A15 cores. It uses ARM CCN504 interconnect that Mike was referring to before. It has the virtual pipeline acceleration technology that I talked about, and it's a rich set of ADKs in the software ecosystem around it. I guess in summary, ARM is enabling many unique solutions across the enterprise space. As we are going through this SD and NFV type of disruptions, ARM has been a great partner for us, and we continue to build ecosystems together, both from a hardware and software standpoint. Yeah. Thank you.
Thank you. The paper is now open for questions. So please step up to the two microphones and state your name and affiliation before asking your question.
Hello, Satoshi Matsushita, NEC. You told that the processor is for the virtual network processing. Does it have some flow table for OpenFlow compatible programming?
Yeah, it is there are two parts to it. There is an OpenFlow data plane, control plane, right? So the pipeline part of it is very natively implementable on Axia because of the OpenFlow, as you know, like 1.3 and beyond, right, or 1.2 and beyond. It's very iterative in nature. It's sort of like a for loop of all the searches and actions, table lookups, all of that. So because of the iterative nature of the pipeline, it's very amenable to implement on Axia because of the accelerators that I've shown you. So the specific instantiation of it, 5516, is already compatible with OpenFlow 1.3. Support all the APIs, both on the control side, SSL and all that, and also on the data plane pipeline.
Okay, thank you.
Okay, let's take a question from the other side of the room.
Stuart Fisk from Cadence Design Systems. I had a question about the L3 cache. It was mentioned that it was an adaptive, inclusive, exclusive policy. I was wondering what you were doing there exactly, what that meant.
So exactly, we should probably talk offline, but the way you can think about it is with the L3 backing fairly large L2 caches, up to 2 megabytes in the A57 and A53, you certainly don't want an inclusive L3. So you can think of it as first order, it's an exclusive L3 with the ability to install some of the cache contents in the L3 depending on sharing patterns and et cetera. So also from the perspective of the I/O devices and accelerator devices, it's certainly an inclusive. Well, it's just a pure system cache. It's not inclusive or exclusive.
Okay, please.
Nikhil Gupta, AMD. I wasn't clear on how the virtual pipeline. Is there a specific? Do you add a function, a processor in there to manage the virtual pipeline, or is that something that ARM kind of provides for that?
It's a homegrown technology internally. It's been there for other generations of Axia has also.
Okay.
Okay. One last question, please.
Zoni from Camp Marketing. I take it the DSP is used to generate some flops for accelerating certain functions. Could you, if that is the case, could you let us know what the DSP is used for as an accelerator in this design? What specific functions are being accelerated by the DSP?
You're asking what type of functions get accelerated using DSPs?
Yeah, I take it you're using the DSP as an accelerator?
Yes, DSP classic case could be a baseband processing, for example.
Baseband processing, anything else? Encryption side, decrypt, compression,
many of these other
functions.
Yeah, many of these other functions that you're talking about have dedicated accelerators. In addition, DSP tends to be used for example, baseband.
Thank you.
All right, so let's thank the presenters again.
Thank you.
The next paper is entitled Applied Micro X-Gen 2 and will be presented by Gaurav Singh. He joined Applied Micro as Vice President of Engineering and was responsible for ARM and PowerPC engineering, platform architecture, and product development for the company's high-speed X-Gen 1 and X-Gen 2 microprocessors. He is currently responsible for technical strategy, which includes definition and architecture of all future processors. Gaurav has worked on multiple CPU ISAs, including x86, MIPS, PowerPC, and ARM. He started his career at AMD, working on the K6 and Opteron microprocessors, designed MIPS-based XLP communication processors at RMI, and PowerPC and ARM v8 designs at Applied Micro. He holds multiple patents in high-performance CPU architecture, Ethernet switches, and switch fabric design, and has a graduate degree in electrical engineering from University of Southern California. Please join me and welcome Gaurav Singh.
Thanks, Stefan. It's a pleasure to be here today. I see the room full, so I'm glad you stuck around this late. So before we get started, just to keep the lawyers happy, basically what it says is that you can feel free to trade in Applied Micro securities, but just don't base it on what I'm about to tell you. So the topic for today, I'm going to go over our roadmap of the X-Gen roadmap, and this is the first time we're actually showing our roadmap, our current products, the products that we're sampling, and the products that we're actually designing. So I'm really excited to be here to tell you about that. We'll quickly review the status on X-Gen 1, where that is, and then I'll dive into the details of X-Gen 2, which is what the meat of this talk is going to be about. I'm going to go over the design targets. I'm going to go over why we did some things the way we did them, the changes from X-Gen 2, and then I'm going to give you guys a sneak peek at X-Gen 3. So this is our roadmap. X-Gen 1 is shipping today. It is in production. It's in 40 nanometer. It's an 8-core, 2.4 gigahertz part. X-Gen 2, or Shadowcat, as we call it internally, is sampling. It is in the lab, and we have sampled it to our lead partners and customers. And X-Gen 3, or codenamed Skylark, is in design right now. So the team is on designing Skylark. Skylark is where we go with much larger core counts, and it's also going to be on 16 nanometer FinFET. And it will sample next year. This is X-Gen 1 Storm, which is in production. It is Applied Micro's first generation ARM v8 CPU. And if you've been following this space, it is also the first server-class ARM-v8 CPU. We started designing the CPU concurrently with the architecture from ARM. It has 8 cores running at 2.4 gigahertz, 8 megabyte L3 cache. It has 4 DDR memory channels, lots of PCI Gen 3 interfaces, SATA interfaces, fully integrated 10 gig interfaces with integrated NICs, and integrated system management. We also have, in the corner, you can probably see the platform management. So effectively what that is a small Cortex processor that can do things like reset, power management. It can do secure boot. So we have had this capability for a while in a lot of our embedded parts, where we are able to wall off and establish a secure root of trust and make sure that all of the authentication of the software layers on top of that happens over that processor. So we have that in XGene-1 as well. We have lots of accelerators. I could be here all day talking about the accelerators that we have, but just to summarize, we have security accelerators, networking, and scale-out accelerators. You can probably see the diagram there that talks about the network interface. What we have the ability of doing is classifying packets as they come in. Packets come in, we parse them, we can classify them. We can classify them into flows, and then we also have traffic management capabilities on top of the flow. And all of that can be done inline to the packet. You'll see a blue box that says on-chip memory. So we also have the ability of routing packets and data into the on-chip memory. We have offline processing that is not part of the mission-critical ARM-v8 processors that can work on that data. And in certain cases, we can even ship that data out without ever going to memory. So we have lots of unique capabilities in the SoC in addition to the ARM-v8 CPUs. So this is Storm. So where are we with Storm? Well, instead of showing you die shots, I'm going to show you actual products. And you'll recognize some of the products here on the upper left. You'll see a dense system. This can have 45 XGene-1 processors in it. There's a similar traditional 1U system on the extreme right. And this is a 1U pizza box that can have 8 XGene-1s in it. We've also seen a lot of interest in the HPC space. So you'll probably see that silver brick. And it's actually a very interesting design. The silver brick is water-cooled, and it's used in the HPC space. And this is the system that's being designed with XGene today. It has 1 XGene card. It has a Mellanox card for InfiniBand. The HPC guys like to do very low latency MPI-type interconnects. And then it can have multiple NVIDIA K20 and K40 GPUs. And all of that in this tiny little brick, and extremely modular, and extremely high performance. And one of the unique differentiators with XGene and ARM is that you don't need to chill the water. With an existing system today, you have to chill the water. With us, you don't. And that, believe me, that's a pretty big deal in the HPC space. But really, to summarize the point here, XGene-1 is shipping. XGene ARM servers are here. I remember standing on this very stage at a previous Hot Chips and introducing XGene-1. And at that time, I was in a session I was the only ARM presentation in that session. And today, we have a whole session on ARM. So that should give you an indication as to where ARM is headed, where ARM in the servers is headed. So now I'll start my conversation on XGene-2 and what we did on XGene-2. But before we do that, I just wanted to quickly touch and take a step back and talk about the scale-out applications and what are scale-out applications, because both XGene-1 and XGene-2 have been designed for these scale-out applications. To summarize it really quickly, what scale-out applications are applications that cannot run or don't run on the traditional 1P, 2P, 4P servers. They need to run on hundreds of servers. These are applications that the software designers have designed to specifically run on hundreds or even thousands of CPUs. So the question really is that if you step back and say, well, what can you do as a silicon vendor? What can you do as a CPU vendor to optimize for scale-out applications? The thing to observe is that these scalar applications are applications that are, I'm going to define something called an application thread. These are application threads that run on an individual CPU. So the performance of each application thread is of interest. But the second thing about these scalar applications are that they talk to each other over the network. This is sometimes referred to as the east-west communication, because these are all applications that could be working on their own piece of the data, but at some point they have to communicate with each other. So really there's two things if you want to optimize for scalar applications. The first is optimizing the performance of each thread as it runs, and the second thing to optimize is the interconnect. So let's talk about the first one. If you think of an application thread running on a CPU, here the microarchitecture details of the CPU are interesting. Is it an in-order machine? Is it an out-of-order machine? Is it a quad issue? Is it triple issue? What other bells and whistles do you have in the CPU? And that goes to the inherent capabilities of the CPU itself. But the second and equally important aspect is what are the type of resources that can be provided to that application thread. And by resources, I mean things like how much cache, how much memory bandwidth, how much I/O bandwidth can that application thread muster. So the resources that you provide to that application thread are important. Then the second aspect is the networking interconnect. What can be done to optimize the networking interconnect? The de facto standard today is TCP/IP over Ethernet, and TCP/IP has been very robust. But one of the inherent problems with TCP/IP is that the application latency is extremely high. So when we looked at this problem about 3 years back, you can tell from the whiteboard picture, we started, instead of a blank paper, we started with a blank whiteboard. And as you can tell from the picture, my handwriting needs a lot of work. But more importantly, we looked at every new technology that was coming out at that time. And there were a lot of interesting things people were doing at the layer 1. There were a lot of interesting ways, topologies in which people were connecting these as scale-out fabrics. But before we did that, we realized that we had to set the boundaries as to what we're trying to do. So the first thing we said was, let's target the rack level. Let's look at a rack, and let's optimize the rack. The second thing we said was, let's use the existing infrastructure. Now, Ethernet as a standard is de facto. It's like air, it's like water in the data center. And we said, let's just use that. For all of its inefficiencies, Ethernet has a lot of value. And there's critical mass behind that. There's lots of people who are hard at work in optimizing it and getting around some of the limitations of Ethernet. So we decided to stay with Ethernet. And then the most important thing we decided to do was to target the application latency where it mattered. Rather than reducing 500 nanoseconds down to 100 nanoseconds, we said, let's try and reduce what is in the order of microseconds down by a factor of 10. And the last thing we wanted to do was to not change the software paradigm. I did not want to invent yet another software paradigm that we would have to go and invest in. So we said, let's use standard APIs as much as possible. Let's be able to leverage existing libraries and infrastructure. So we picked Rocky. And what Rocky is, or RDMA over converged Ethernet, is effectively being able to utilize the InfiniBand network stack on top of the Ethernet link layer. And if you compare TCP/IP with all of the different sessions that happen of buffer copies and chatty protocols and compare that with InfiniBand, there's a dramatic reduction in latency. And so Rocky has the benefit of being able to use the existing infrastructure, switching infrastructure in the data center, but providing a huge value in terms of latency reduction and bandwidth increase. So to summarize the XGene2 targets, first, we designed it for the rack. We optimized the performance of each application thread. So we spent a lot of time optimizing the CPU performance. It's an out-of-order, quad issue, 2.8 gigahertz CPU, high memory bandwidth per thread, high I/O and storage bandwidth per thread. And then the interconnect latency was really designed to be able to scale over hundreds of CPUs. So here's a picture. Oftentimes we get asked, where do you fit in? Where does your CPU fit in XGene2 CPU? So the green button there is XGene2. So I'm trying to quantify the things that I mentioned in terms of the inherent capabilities of the CPU itself along with the resources that that application thread can get access to. So in case of XGene, as I mentioned, it's a quad issue machine, fully out of order. It has 3 levels, the classic 3 levels of caches. It's got about 1.2 megabytes of cache that can be dedicated to each application thread. And it has lots of memory bandwidth. In contrast, if you compare it with the designs on the extreme right, and those are high-performance machines as well, with actually, if you compare a similar memory footprint, but they're much higher frequency. And so those designs come at a higher cost in terms of power and in terms of dollars. Then on the extreme left are the sort of the simpler machines, and these could be dual issue or triple issue in-order pipelines. The class is sort of the embedded 2-level cache hierarchy. But then if you look at the resources that each thread would get, it's a small 400 kilobytes. There's not a lot of memory bandwidth there. So really what we targeted to do was to what we believe is the sweet spot where if we optimize the performance of each application thread and optimize the network latencies, it overall has a huge benefit in the overall application performance. So this is XGene 2. It's our 2nd generation ARM-V8 CPU, 8 cores running at 2.8 gigahertz, 8 megabytes L3 cache, 4 DDR channels, lots of PCI Gen 3, lots of SATA Gen 3, 10 gigabit Ethernet interfaces, all of the system management, secure boot that XGene 1 has. And as I mentioned, it has integrated a Rocky HCA. And the other thing I want to mention is that it has support for NFV and SDN. And some of you might think, what has NFV got to do with it? Because NFV is network functional virtualization, and that really happens at the high-level application level. But really what we paid a lot of attention to was making sure that the hypervisor support, or that virtual machines could run, or the virtualization infrastructure could run in a very efficient manner on XGene 2. So we have full support for hardware virtualization, both on the CPU side and on the I/O side. So there's a system MMU. And both of these virtualization constructs have very good hardware capabilities to be able to go and do page walking, to be able to fetch pages. And so when a hypervisor runs on this, it gets very good performance. In fact, we're starting to see that on XGene. We see that on XGene 1 as well, where the hypervisor overhead on XGene is, in certain cases, even lower than what it is on x86 machines. And this is based on a talk that folks from Citrix Zen had done. So that is XGene 2. So I'll quickly go over the changes that we made to the CPU. But to remind everyone, our architecture really has 2 ARM-V8 CPUs with an L2 cache, which we call a processor module. And we can stamp out multiple of these processor modules connected to our coherent interconnect. And each of these is an out-of-order quad issue, can handle over 100 instructions in flight. It has full hardware support, virtualization support, full slew of ACPI, power down modes, the cache hierarchy, as I already mentioned, and then it's full end-to-end RAS. So we not only have ECC and parity where it matters on the memory, but we also have end-to-end data poisoning and error isolation, which is very important because once you have an error, it's OK to be able to correct it. If you have multiple errors, it's OK to be able to detect it. But how you handle that error is of importance. And we have a very sophisticated mechanism that's spread out throughout the SoC. So the changes that we made to the CPU, I'll hurry up now. On the instruction side, the branch unit got a lot of focus. So we increased the size of the BTB, the branch target buffers. We increased the size of the conditional branch predictors and the indirect branch predictors as well. A few things that we did was, in general, we clean up. We are able to clock gate more flops, a lot more fine-grained clock gating that can happen dynamically. We also added higher trace compression. Now, trace compression isn't something that an application would see, but it's very useful when you're debugging your code. So we can compress the instructions and stream it out onto a serial interface for people to debug their code. On the scheduler side, we increased the number of instructions that we can handle in the scheduling window. So we double the size of the branch and the integer schedulers. And then on the data side, we beefed up the prefetchers. So we had very sophisticated prefetchers on XGene 1 built in already, which could do stride prediction. We could both forwards and backwards. But we basically added the support for more streams that the prefetcher can prefetch simultaneously. And we also added support for larger stride patterns. The other thing we did was so XGene1 and XGene2, if you've not noticed, is that it's a very high frequency. So in order to get that high frequency, we have a semi-custom design methodology. And so we have circuit designers who actually optimize the macros. We design a lot of the hard macros ourselves. We have custom data paths. And so one of the things we were able to do on XGene2 is to reduce the Vmin on the RAMs. So all of the caches can now operate at a much lower voltage. And again, that translates into lower power. Along the same lines of the circuit design, as we go to 20 nanometer to 16 FinFET, and this is nothing unique to us, I'm sure all of you find that as well, there's design challenges from device variation. So the devices tend to vary. So the paths that you thought, if you use the traditional methods for timing closure, the paths that you thought you had passed might actually fail on silicon. So what we've done is we've come up with our own way. So typically the way people take care of that is they have more corners, they characterize the cells over the corners, and run a lot of the timing closure at all of the corners. What we did was we did that, but we also did some intelligent analysis of the top critical paths. We characterized the cells based on, and figured out the process and voltage sensitivity of the cells, and we made these rules. And we said, well, this combination of cell and fan-out cannot happen, or this input slew rate and that output slew rate cannot work with these cells. So overall, these are the ways how we got the high frequencies. And by the way, when we mention the frequencies, those are the frequencies that we're shipping at, right? So there's a big yield at those frequencies. So 2.4 gigahertz on XGene1, 2.8 on XGene2, and 3 gigahertz on XGene3 are really the middle. They're not extremely on the right of the bell curve. Again, Rocky features that we have on XGene2. It is fully verbs compliant. And for those of you who don't know what verbs is the standard API interface for InfiniBand, for RDMA, which means that we can work with any of, and there's a lot of infrastructure already out there. There's a lot of software infrastructure that's already out there, a lot of applications that have been written with the verbs interface. We do that today, and we're completely compliant with that interface. We have full support for the critical RDMA send and atomic operations. And our host channel adapter is on both the 10 gig interfaces. So we get an aggregate of 10 gigabits per second of Rocky interconnect. What we also did was we extended the capability of Rocky to be able to operate across a layer 2 network. So it's sometimes referred to as routable Rocky. So we have our own version of routable Rocky. We're working with the standards. So as soon as there is a standard around it, we will support that as well. But today, there's no limitation into the networks across which Rocky can be deployed with XGene2. So what does this mean? I spoke about application threads. I spoke about the performance of the CPU. I spoke about the resources that the application thread would get. And then I spoke about the interconnect between the application threads. And here's an example 42U rack, because we were designing for the rack. With XGene2, we can pack over 6,000 of these application threads in one rack. Lots of memory bandwidth with Rocky interconnect. The other thing that Rocky allows us to do is, because of the low latency, it allows us to come up with very interesting storage solutions where you can have a disaggregated set of JBODs, but they look and appear as though they're local and directly attached storage. But an example here, and I've taken Memcache, because Memcache is one of the applications that we were able to readily modify to work with the verbs interface. With an XGene2 system, we get about 750 million transactions per second. And this is at TP95. So in Memcache, latency is important. So what that means is that at 40 microseconds, 95% of your transactions should be below that. Whereas with the current server, it's about 400 million, actually it's even less than 400 million transactions per second. What we did over here was we have the current V2 parts, and there's E5 V2s. What we did was we assumed that the V3 parts, which we don't have access to, will see a 25% boost over the performance of the V2 while the power remains the same. So that is what XGene2 can do. More performance. Again, this is compared to our first generation XGene1. In terms of spec 2006, there's a very healthy improvement in performance per watt. On the lower left is Memcache. And this is, again, at a different point. This is at 30 microseconds. And as you can see, XGene2 is double the performance of XGene1 It has a slight advantage in terms of frequency, but most of that is really because of the RDMA. And then on Apache Bench, which is a classic web server benchmark, again, there's a very healthy improvement. So XGene 3, or Skylark, as we call it internally, the team is hard at work. This will be our 3rd generation ARMv8 CPU. There will be further microarchitecture enhancements to XGene 2. But one of the biggest things that we're doing here is we are beefing up the coherent interconnect to be able to handle lots of cores. So we can handle, the architecture will scale anywhere from 16 to 64 cores. Our first product will be somewhere in between, but we will have lots of cores. And this will be on 16 FinFET. And the frequency that we plan to hit in volume is 3 gigahertz. So we're really excited about XGene 3, which is going to be our FinFET part, and it will sample next year. So to summarize my talk, XGene 1 is here, it's real, it is shipping. XGene 2 is sampling, it's in the lab, it's with our key customers, and XGene 3 will sample in a year's time. So that's my talk. Thank you.
Thank you. The paper is now open for questions, so let's start from this side here.
Trivikram from AMD. I had a specific question about XGene 2, the block diagram of the CPU core. If I understand it correctly, it's not multi-threaded, is it?
That's correct.
And I saw that it was a 4-wide core, 4-wide decode, 4-wide issue. And considering that this is actually specifically targeted to the scale-out market, I was curious what made you choose the 4-wide design point without multi-threading?
OK, fair question. So in terms of the issue itself, you have to remember that it's not just integer issue, right? When you say 4 issue, the 4 issue could be a combination of integer, could be a combination of load store as well, right? So in a high throughput design like scale-out, where you want to get data in and out, you want to be able to fetch instructions, so there's loads going on, right? And since it's a completely out-of-order machine, the machine itself can extract the instruction-level parallelism out of the code, right? I guess if your point is that going from 3 to 4 instructions...
Well, that kind of answers the question. So how's that 4 split? Is it 2EX, 1 load, 1 store? Or?
Well, so there's actually any combination. We have 7 functional units. There's multiple loads. There's a branch unit. There's floating point unit, load store. So I think it's in the diagram. Actually, if you look at the CPU diagram, you can actually see them laid out.
Sure. OK, thanks.
OK, let's go to the other side of the room.
Peter Shu, Oracle Labs. What is the power dissipation of the XGene 2 chip?
Of the XGene 2? So we're not disclosing the power, but I can tell you the sweet spot as we see in the power is anywhere from 20 to 40 watts. And that comes more from the type of systems that it can go to in terms of the form factors that it can go to. So it's somewhere in that range, but I can't give you an exact number.
Can you say for XGene 1?
It's in the same range.
All right, on this side.
David Cantor. So I have a question about the RDMA.
OK.
Can the RDMA be sourced from and placed into your cache, so bypassing memory, and if so, at what level?
Yeah, so that's a great question. So we've, I guess people call it direct injection. We call it stashing. And we have the capability to today, even on XGene 1. So even on XGene 1, any data that comes in on any of the interfaces can be written directly into our L3 cache without really having to go through memory. And so the same is true for RDMA as well.
And so that's fully coherent then?
Well, so there's an address translation there's an address translation widget that happens in the middle, but yes.
Thanks.
Andrew from Huawei Technology. XGene supports the network accelerates. Is it hardwired or microcode based?
OK, so I'm trying to figure out how much I can say. I can tell you that there are lots of hardware widgets along the way, which we can do inline. So when the packet comes in, there's inline classification and parsing that happens. The classification and parsing is programmable.
Okay.
But so think of it as a programmable state machine.
What about for the OS features?
I'm sorry?
OS features.
Yeah, I'd rather not give details on that, but there's some few things that we put in for OVS.
Okay, thank you.
Okay, the last question, please.
Can you say approximately what you think the power dissipation would be for the fully loaded 42U rack with the X-Gene 2? The whole rack.
There's an indirect way of figuring out the power. Well, so I can tell you that it's not, so in terms of racks, there's many different levels, and this is going to be upwards close to 30 kilowatts.
Okay, thank you.
All right, let's thank Gaurav again. Thank you, and that completes the ARM servers session.